Morning, class. Hope you guys had a good weekend. So if you guys have gotten hopefully you guys have gotten the message that the second homework assignment has been handed out. I have, so second assignment is due on the 23rd of this month. So next Wednesday, the 23rd. Okay. So let me go ahead and write that down before we get started with today's lecture. So I'll put it here. So today is the 14th, chapter 2 homework due on the 23rd. Okay. So the plan is going to be to chapter 2 will take us all of today's lecture and probably a part of Wednesday's lecture as well. Okay. I know there have been requests to put you schedule up for you guys, and this semester, I think, just because of the start of all the new technology, we're currently we're about 2 lectures behind from where I usually am this time of the semester, but I think we'll end up. I have a few ideas for how to kind of make up that time, but it shouldn't impact you guys in terms. Well, the only change I will probably make is when we have the review for the exam, I will host a separate review session that will be handled by one of the TAs, but and let me kind of give you a sense of when when I'm thinking of having the midterm one. So I'll put the word tentative date for midterm one. And I will post this stuff, but the tentative date for midterm 1 is going to be the 12th. Yeah, so it'll be the 12th of October. And so then I'll have a review that I'll share with you guys. Usually I try to do it at least 2 weeks earlier. I'll try to do it more than 2 weeks, but you'll have it at the latest by the by the 28th of September. And I'll give more details as over the next coming lectures. Okay. So if you haven't logged into your iClicker app, go ahead and do so. We're going to be doing a few of those questions a little bit later today. Well, I want to go ahead and get started. So today's, we're going to move on to the next topic in chapter 2, which is acceleration. And we're going to learn how to also convert motion diagrams and look at different types of plots to extract information. But this topic of acceleration builds on previous concepts that we've learned. So previously, just to recap, we've got things like displacement given by the final minus the initial positions. We have discussed velocity. And so we know that velocity, and in this case, these are all vector quantities, but velocity is given by the change in your position or by the displacement over a time interval. And so this, like I said, is called velocity. And today's lecture is going to largely deal with a new concept that we're calling acceleration. And acceleration is going to be the change in the velocity over a time interval. So each of these has units associated with them. For displacement, the units that we use are meters. We use the symbol m. For velocity, the units are meters per second. So the units the abbreviation, the SI for this SI unit is, m per s is meters per second. And so if you keep,
Excuse me.
yeah, go ahead.
Are you sharing your screen because I can't see anything?
Oh, great. Thank you for saying something because, we could go the entire lecture like this. Thank you for that. So here we go. So you're just looking at my big face talking about stuff. Sorry about that. All right, so you can see my screen now?
Yes, thank you.
Thank you. All right, so on the right-hand side of the slide are some of the dates that I mentioned. So homework 2 due dates, tentative date for the midterm, and when I'll share the review with you guys. So right now we're just doing a recap on concepts we've covered. I've defined displacement, velocity. And so as I mentioned, today's main topic is this concept that we call acceleration. And so if you look at what we're dividing here, well, we're dividing velocity, which we know has units of meters per second, and we're dividing by seconds. So this is essentially meters per second per second. But because we don't like to write with too many of these slashes, another way of writing it, and which is the accepted way, is to write it as meters per second squared. So that double division by seconds shows up as a meter squared term, okay? And so, and I emphasize this because it is important for you guys to check that when you're doing problems that your units come out to what they should be. It's just a little bit of a hint letting you know that maybe you did it right, or if your units are off, that maybe you did the algebra incorrectly. And so what does this mean? Well, so this concept of acceleration is looking at how velocity is changing. And so this is the type of concept that's most relevant when you're speeding up and slowing down, because that's essentially what we're doing. And so on the table here on the right, we have some specifications for two different kinds of cars. So we've got a Corvette that can do 0 to 60 miles an hour in 3.6 seconds. Whereas if you compare that to a Chevy Sonic, which is a much smaller car with a much smaller engine, the best it can do is 0 to 60 miles an hour in about 9 seconds. So you can see there's a difference of, so the Corvette can speed up to 60 miles an hour almost 3 times faster than the Sonic can. And so these numbers, you can use them to calculate acceleration. So for example, so for the Corvette, so if we wanted to calculate acceleration, I'll start using the actual symbol. We know that it's going to be some change in velocity over delta t. And if they tell us that it can do 0 to 60 miles an hour, in this case, the initial velocity is 0. Final velocity is whatever 60 miles an hour converts to in meters per second. And on the slide, they don't calculate it exactly. Well, they don't tell you the conversion factor, but it turns out 60 miles an hour is equal to about 27 meters per second. And then it also tells you that it can go from 0 to 60 miles an hour in a time of, and we'll call this our delta t, of 3.6 seconds. So if you were going to figure out the acceleration, you would just say, okay, well, the final minus the initial velocity over delta time. Since we started at 0, then really it's just final velocity that goes at the top. So that part here goes to 0. So we've got 27 meters per second divided by 3.6 seconds. So if you do that calculation, you'll get a number in units of meters per second squared. And so for this problem, it turns out that when you do 27 divided by 3.6, you get 7.5 meters per second squared. And so you could do something similar for the Sonic, and you would learn that it's a much lower acceleration. So hopefully, so really what's happening in this case is, because we have this acceleration of 7.5 meters per second, you can say if you were going to write this down in English, in the first second, you increase by 7.5 meters per second. So you go from 0 meters per second to 7.5 meters per second. During this second, so between 1 second and 2 seconds, that means we're going to go, we're already starting at 7.5, and now we're going to add another 7.5 meters per second. And so that would give us 15 meters per second by the end of the second. So this 15 meters per second is what you get at 2 seconds. The 7.5 is what you get at 1 second. And you can keep doing this. So you could say, between 2 seconds and 3 seconds. Now we're at 15 plus 7.5. And so that's going to give us 22.5 meters per second at the 3 second mark. So you can kind of just go second by second to see how this works. And obviously, as time goes by, you keep getting faster and faster. So this next problem is going to ask us to use acceleration to figure out this problem. So in this problem, it says lions, like most predators, are capable of very rapid starts. It says from rest, a lion can sustain an acceleration of 9.5 meters per second squared for up to 1 second. So basically, it can go 1 second maximum time at this value of acceleration. So essentially, it's a real live creature. It gets tired, right? Its muscles can only give you that quick leap for like a second. And so this is why, even cats, right? And many predators, you have to sneak up on your prey, because even though you can move super fast, I have a cat that can swat flies out of the air. They're fast, but they can't do that nonstop. And so in this case, they want to know, how much time does it take for a lion to go from rest to a speed of 10 miles an hour? So in this problem, they want to know what is the delta t for moving from rest, so initial velocity 0 meters per second, to final velocity of 10 miles per hour. Okay. And so I've already told you we have this equation, right? That acceleration is delta v over delta time. In this case, because we want to find the time, we know we have to rearrange this so that we get an expression that says that time is equal to your change in velocity over your acceleration. So we know that in 1 second, it can get up to 9.5 meters per second in velocity. So the first thing we really want to do is to find out, well, what does this final velocity that they're asking about translate to in meters per second? And so there's a calculation that they show here on the screen, but basically it means that that final velocity is 4.5 meters per second. That's what they're asking, is how long is it going to take for it to go from 0 to 4.5 meters per second, all right? And so in this case, like I said, we're going to take our, what did I get the, yeah. Okay, so what that means then is we're going to plug that information into this expression. And so delta t, which is change in velocity, if you remember now, is final minus initial velocity over acceleration. But we said the initial velocity was just 0. So in this expression, we're just going to have 4.5 meters per second minus 0 over the acceleration of 9.5 meters per second squared. So essentially 4.5 divided by 9.5 is going to give you roughly half, or 0.47 seconds. which is good, meaning that it can actually get to that speed. And it's still, that lion still has a little bit of juice in him, right? He can still go a little bit faster if he wanted to. And so in other words, what they're saying here is that it can get to that speed in half a second, which is pretty freaky. I mean, this is the reason why, if lion successfully manages to, stalk their prey and get really close, it just takes a half second for it to speed up super fast, and before the prey knows it, I mean, it's been caught. So this is a quick example of how to use that expression. I mentioned in the previous slide that you could start plotting the different speeds. So in the previous example, we were looking at the very bottom. We were looking at this kind of just thinking about it in our heads a little bit of, well, what would your speed be at every time interval? And so what they're showing in the graph on the right here is just tabulated data for a Sonic versus a Corvette. And so what we're going to look at now is the velocity versus time graph for the two motions. So this is a Corvette versus Sonic. And so in this case, you can see how, if you start with that graph, and this is, so we'll call this our velocity in the X, which is in units of meters per second over the time. Then for the Corvette, we said at 1 meter, or at 1 second, the velocity is 7.5 meters per second. And so this matches what we had written here, right? The 7.5, 15, 22. Well, they just wrote them down for us on that table. So we can just copy that down here, say, okay, here it's 7.5. And then at 2 seconds, we're at 15. At 3 seconds, we're at 22.5. So on and so forth, right? You can see the rest of the numbers here. But the point is, we're just collecting the information every second, but you could have even collected in between at times in between, and you would find that you get this nice kind of linear relationship between the velocity and the time. And so, and this curve would be for the Corvette. And then for the Sonic, it has a slightly more shallow slope, right? In this case, after 1 second, you've only gotten to 3.5, or yeah, to 3, and then 6, 9, 12, etc. So in that case, that one's going to have a much shallower slope, kind of like this. And so it turns out that one of the things that we are going to find here is that the slope of a velocity versus time graph is going to give us acceleration. And so hopefully it makes sense that we know this, because slope, if you remember, rise over run, right? Whatever the vertical over the horizontal value is in the graph. So maybe instead of vertical and horizontal, that's a little bit misleading. Let's actually write down here. Really, we're looking at the y-axis versus the x-axis, right? It is vertical and horizontal, but I don't want to imply a actual physical position necessarily. And so what this means is on the y-axis, well, you look at your units, that's meters per second. On the x-axis of this graph, it's the units per second. So you can see clearly the units end up being meters per second squared, okay? And so for this particular example, we can see very clearly, just as before when we're doing position versus time, giving us the slope, giving us velocity. In this case, in velocity versus time graph, the slope of this graph is going to give us acceleration. So it's a very analogous relationship to the previous stuff we've talked about. And so what that also means is that you can obtain accelerations from velocity graphs by just looking at the slope. So in that case, if we were to take another example here that's using this idea of a slope, using slope of a velocity versus time graph. If we start off with a plot like they're showing on the slide here, and I'll try to color code just to make it similar to what they're doing here. You might have a velocity graph where you have a very steep slope and it goes to 0, and then it decreases kind of slowly like that. In this case, they just put some marks there that don't mean a whole lot yet. But the idea is if you were to, from a velocity versus time graph, produce an acceleration versus time graph, you just have, it's essentially just a plot of the slopes. So to go from velocity to acceleration, so instead of using slope versus time, I'll put to obtain acceleration. So what we're doing in this case is we say, okay, well, in this plot, we know that in the first part of the motion in this velocity graph, that's going to be the steepest slope, and it's positive. So we know we're going to have some sort of value that's sitting kind of high up on that graph. And so we'll have, and it's a constant slope, so it'll be a constant value. And then when we get to this point, all of a sudden we see that the slope is 0. So that means our acceleration has to be 0 in the entire time that our slope there is, flat. So we get something that looks like this. And then finally, we see that in this case, the slope is negative. So this was a positive slope, negative slope. And so, and it's going to be a little bit more shallow. It's not as steep as a positive one. And so we know we're going to be down here and maybe not as high in value. So whatever this number was, let's just, because it's half the incline according to that graph, then, and I'll go ahead and label that little dot here just to make it identical. Well, we know that because it's half the slope, then the value will be negative and it'll be half the value of the first one. So it'll be about right here. It'll be a constant value up until that point where we cross the A=0 line. So we get something that looks kind of like this. So in this case, we went from a velocity versus time graph to an acceleration versus time graph. So v versus t to acceleration versus time. Okay. So we also need to remember that these are all vector quantities. And anytime you've got these vector quantities, so just looking real quick at the expression that we have for acceleration, I'm going to write it down one more time. So it's acceleration, final velocity minus initial velocity. Remember that those are vectors. All this divided by delta t. That's what we're used to seeing. Well, at the same time, you can think about this in many different ways. You can think of that delta t as just being a factor that you're multiplying your vectors by. So really what we're doing at the end of the day is we are just subtracting two vectors to get acceleration. And then we multiply it by this constant of 1 over delta t. And so what that means is in the problem that we have here for the quick check, let me go ahead and start it for you guys. It says here we have a particle with velocity v1, and as it moves from point 1 to point 2, the entire time during the motion, so at this position number 1, this is where we have our initial point. And at position 2 down below, that's going to be our final position. And so this entire time, what we're doing is we've got we're working against an acceleration that's going in the opposite direction, and our velocity is in a direction that's downward, okay? So we got something like this. That's our initial velocity, or velocity 1. What they want to know is, what is velocity 2 going to look like? Well, mathematically, you can rearrange this to solve for the final velocity. You could do that. So you can have, basically, it'll be some acceleration times this factor of delta t plus initial velocity is going to give you the final velocity. That's one way, certainly, of looking at it. Another way that I think is a bit more intuitive is anytime you see this acceleration, think about it, something's causing it, right? Something is causing the acceleration. You know, something is changing the velocity. So we're not going to talk too much, at least yet, about the details of what is this something, but just imagine that there is, you know, something's pushing on it or pulling. And later on, we're going to discuss that this is actually a force. But anytime you see acceleration vectors, just remember it's something kind of pushing in the direction of that arrow. So if you have an initial velocity that's pointing downward, and you've got this arrow that's pointing in the opposite direction. Now, I've done it a little bit of a disservice by not making them to scale, but in the picture, you can see that the initial velocity vector is actually, it's considerably longer than the acceleration vector. So that means that this acceleration is pushing in the opposite direction. So when you get to position 2, you're going to end up with a velocity vector that's a little bit shorter than what you started off with, because it was pushing against it. It's like pushing on the brakes in your car. You might be going one direction pretty fast, and then you decelerate. That means a negative acceleration. And so what happens in those cases is you don't immediately go the other direction. You just slow down, right? And you can imagine if there was a push against you that lasted long enough, eventually you would start going backwards. But in this problem, because of the size of the arrows, because the acceleration vector is considerably smaller than the initial velocity vector, you're going to get a situation where your arrow just gets a little bit smaller. So vector answer B is the correct answer, where your arrow just gets a little shorter. And the other options, you actually have it going in the opposite direction. And the first one, there's an increase in the velocity. Okay? So let's look at this just to make sure that we all remember how to read motion diagrams. So in this problem, they're showing you velocity vectors in green and then the acceleration vectors in orange. And all of this is superimposed on a number line. So it says here, the motion diagram shows a particle that is slowing down. The sign of the position X and the velocity V are, and then you get to choose. So first thing is they're asking about position, and then the next thing is they're asking about velocity. So let's think about the question about position. Well, for position, a lot of B's, so it looks like maybe you guys already know. Well, for position, all you have to do is look at all the points. So we've got points that are all to the right of the X equals 0. So this is position X. So these are all positive. So we know it's going to be either A or B. Next question is velocity. Well, for velocity, all we have to look at is whether they're going to the left or to the right. So for velocity, they're all pointing in the negative direction. So these are all negative. And so that means from those choices, option B has to be the right answer. Okay? So, all right, let's continue. So in this problem, So it's a little bit conceptual, and it's kind of leading up to some of the quick check problems that are coming up next. But here it says we have a ball moving to the right, and it's going to traverse the ramp shown below. And they want us to sketch a graph of the velocity versus time, and directly below it, using the same scale for the time axis, sketch a graph of the acceleration versus time. So first thing, let's actually draw this figure or the problem. So we have this little ramp here, nice and flat. It's going to go down at some angle, and then it's going to go flat again. Okay. So, and they tell us that it's starting off with some initial velocity. So the V0, you could think of it as V initial. It's just saying it's greater than 0, so it's positive. It's going like that. So in this problem, it says to graph the velocity versus time. So if we decide that the starting point where they've drawn the ball is equal to the time equals 0, let's try to do something like this. That's time, and this is velocity. So in first case, well, there's going to be a few places where there's changes, right? When you get to that ramp, something's going to change the velocity. They don't say it explicitly, but let's just assume there's no friction. So friction is that thing that would slow the ball down. So in the first part, we have velocity greater than 0. There's nothing really to slow it down. So we would expect to measure a positive value of velocity equal to that initial velocity up until we get to that point. Now, when we get to that point, we're going to start going down the ramp. Initially, the velocity will start going in the, it's going to start going down. In this case, we're mainly interested in, so this, and I should say this is velocity in the x direction, okay? So in this case, that's what we're plotting. So when we get to this point, well, we know the velocity is gonna increase. By the time it gets to the bottom of the ramp, that velocity might be a much larger vector. However, since we're plotting velocity in the x direction, we're interested more in only in that component of the velocity. So on this graph here, we know this, these vectors that I've drawn, which is the true motion of or the true velocity. Well, those velocities are made up of this x component and the y component of the velocity. But we're mainly looking at just the x component. So if you look at the x component, at the beginning of the ramp versus at the end of the ramp, you see that that number gets larger and more positive. So in this case, you would expect, and it's gradually increasing, right? So we would expect in this case, and I'll do a different color just so that it stands out. So we had initially, we were here, and then now, at this point, our velocity is going to be increasing to a higher x component. And then finally, when we get to the bottom of the ramp, well, the rest of the motion here, this is all flat. So we can say that that new velocity, which we'll call the final velocity, well, it's a constant. It's not changing anymore. And so for the rest of this motion, we get this nice horizontal constant velocity we can call the final velocity. So in this case, that's how the velocity in the x direction would change. The next part of this problem asks us to draw an acceleration versus time graph. So in this case, this is how you'd make another graph right below it. So this is time, and now what we're going to be plotting is acceleration. Remembering this is meters per second squared. And so the thing that we got to remember is slope of velocity versus time gives us acceleration. So in this case, you start off here, constant velocity. Well, that's actually constant, well, it's a 0 slope. So the acceleration in this first part of the motion is actually 0. zero acceleration down here, a equals 0. Next part, we have a positive slope to the velocity. So for this motion, and it's a constant slope, so it's a constant positive acceleration. So you'd have something that's up here in the positive y-axis. And then finally, when you get to the end of the ramp and you're going flat again, there's no more change in velocity, slope is 0. So you get back to 0 acceleration. And so this is what an acceleration versus time graph would look like for this problem. Keep in mind, so as you can see very clearly, you can be moving at a constant speed and have 0 acceleration. The analogy with this is when you're driving on the highway, if you're going at a constant speed, technically you're not accelerating, so acceleration 0. And I think that's something that might seem a little counterintuitive, but that's just how it works out. Just remember, acceleration has to do with change in velocity. So in the slide that's shown here on the right, it says an object can move right or left or up and down while either speeding up or slowing down. Whether or not the object that is slowing down has a negative acceleration depends on the direction of motion. So in other words, there's two ways. You can have two types of motion that have the same acceleration, is another way of saying that. So the picture that you see here on the right shows what those two types of motion could be. So in one case, you could have a situation, I'll just put this number 1, where velocity starts off low, and then it starts getting a little bit more positive, and more positive, and more positive. And in this case, well, because the velocity is changing in the positive direction, well, that means that we have a positive acceleration to the right. But you can also have a situation in which your velocity starts off maybe kind of large with a high value. And as time goes on, the next time point shows a smaller velocity, and a smaller velocity, and a smaller velocity. Well, you know, if you remember back the example we talked about, where I mentioned to you, anytime you see acceleration, just remember there's something pushing in that direction. In the first case, it was pushing in the direction of the velocity, so it just made it speed up. In this case, the velocity vectors are getting smaller. The system's slowing down because the acceleration is pushing in a direction against the velocity. But in both cases, it's the same acceleration. The acceleration still has the same value. So one thing that we can write, and this is something that might take a little while to sink in, but it is that acceleration always points in the direction of changing velocity. And the key word here is changing. You have to see how the velocity is changing. So, and so you might seem a little bit strange or maybe counterintuitive. And one question could be, well, how does that affect the velocity versus time graphs? Well, in this case, if we look at the velocity versus time graph, keeping in mind that the slope is going to tell us about acceleration. Well, in the first case, you start off with a low value, you know, some kind of sort of positive velocity that over time gets more and more positive. So in that case, we're tracing this line that has a constant slope that's positive, which is kind of what the drawing indicates. If you look at that same, the velocity versus time graph for the bottom situation here, number 2, well, the main difference is that you start off with a much more negative velocity. So instead of being close to the v equals 0, we're way down here. It's very negative. But at the next time point, it's a little bit less negative, and then less negative, and less negative, until it looks like it's approaching 0, right? That's what we see in the arrows. The arrows keep getting smaller and smaller. So in that case, we're tracing out this line, but once again, slope gives us the value of the acceleration. So in this case, even though you're moving in opposite directions, because of the way that velocity is changing, you get the exact same positive slope in both cases. So that's kind of cool, I think. Turns out that, well, the acceleration can be in the other direction. And then in that case, you get sort of the exact matching counterpart to what I just described. So in the first situation, we had going to the right and increasing, going to the left and decreasing. Well, you can go other way around to say, okay, well, maybe now, so let's call this situation number 3, where you start off high with a large positive velocity that gets smaller and smaller. Well, in this case, we know that something's making it get small, so it's working in the opposite direction. So in this case, you'd have your acceleration going to the right. I mean, yeah, to the left. You can have another situation where you start off from the other end, but except now you are making your velocities more and more negative. So the magnitude is changing and it's getting just really big, but in a negative direction. Well, in this case, because you're making the velocity grow in that direction, well, the acceleration has to be in that direction to help it get larger. And then you'd learn that you get similar types of graphs that have, so the idea in this case is you're gonna have the same slope in both cases. In the first case, if I just do it again, as we did for the first 2 examples, velocity versus time, well, here you start off highly positive, and then now you're less positive, less positive, less positive, and you're starting to approach a 0. So there's your slope. Once again, negative slope, negative direction for acceleration. And the second example, something similar where you start off just a little bit negative. This is velocity versus time. And then you get more and more and more negative as time goes by. So you trace out this line. And once again, you see those 2 slopes are the same because it's the same kind of acceleration. All right, so this slope is telling you that information. So let's see if we're getting everything we're talking about. It says here, the motion diagram shows a particle that is slowing down. The sign of the acceleration, a in the x, is, well, what is it? So, I mean, even if they didn't show you the acceleration vectors, hopefully you can see just by the green velocity arrows that we're starting out on the right-hand side with a very large negative velocity that's getting less and less negative. So that means if you were to make a plot for this quick check 2.15, it would look a little bit like this. We have velocity, time. We start off highly negative, so that's down here. And then we're getting less and less negative. So it would look a little bit like that. And, you know, then if we actually look at the acceleration vector, you see it's positive. And so in this case, many ways of thinking about it, but we find out that the acceleration is in fact positive, okay? So, all right, so now you have to think for a few steps, but it's a similar way of thinking. It says here, a cyclist riding at 20 miles an hour sees a stop sign, then actually comes to a complete stop in 4 seconds, then in 6 seconds returns to a speed of 15 miles an hour, which is the correct motion diagram. So first thing I would say is okay, well, he's moving at 20 miles an hour, and because they're, you know, we can assume that it's a positive motion. There's nothing indicating that it can't be. So we know we're starting with these arrows to the right. You see a stop sign, and then, well, as you see the stop sign, well, you're gonna have to slow down. So these are all velocities. And it says it comes to a complete stop. So at some point, these dots just have no velocity vector according, you know, related to them. And then finally, it says that in 6 seconds, returns to a speed of 15 miles an hour. So we're gonna start speeding back up. but we may not reach the original size. So in this problem, this very first velocity may have been 20 miles per hour. The final velocity is going to be something like 15 miles an hour. And in between, there was a slowdown of the motion. And so if you look at the velocity vectors, there's some that do that. You have to make sure it's large velocity on the left, smaller velocity on the right. And you have to make sure that the accelerations are also matching. So in the first part, what can we say about the acceleration? Well, it's slowing down, so it's moving in the opposite direction. Finally, when we get to zero, or to no velocity, and we sit there for maybe a little bit, there's not a whole lot of velocity, but then after a while, we start speeding back up. And so now your acceleration arrows are getting bigger, or your acceleration vectors are pointing in the opposite direction to the right to help it speed up again. So we had two changes in the acceleration. And so as most of you correctly answered, B would be the best choice. So the velocities have to match reality, and accelerations so also have to change. So let me know if there's any questions, okay, guys? All right, so I'm gonna go ahead and skip this one. Let's do this one now. So in this quick check, it says, Mike jumps out of a tree and lands on the trampoline. The trampoline sags 2 feet before launching Mike back into the air. At the very bottom, where the sag is the greatest, Mike's acceleration is blank. Is it upward, downward, or zero? So think about what's happening to the Mike's velocity. Also think about what is causing the change in the velocity. What is pushing Mike towards that trampoline? And then eventually what's, he's gonna move back up. So I like it when it's everybody matching answers. So what is gonna happen? Let's look at this kind of step by step. They wanna know what is the acceleration at the bottom. All right, so for a quick check, 218, we know what is acceleration at the very bottom. So, I mean, there's various ways of thinking about this, but let's say that I'm gonna put the, so he's starting jumping out of a tree, right? So if we've got a little tree here, and there's little Mike, crazy Mike, he's gonna jump out, and if we start drawing the velocity vectors, and down here is where we have our little trampoline. Well, what's going to happen? Initially, we know that the moment you jump out of your tree, your velocity is going to be pretty tiny. Over time, you're going to be speeding up, speeding up, speeding up, until you get to the trampoline. And then at the trampoline, well, you're going to slow down a little bit, right? Until the trampoline reaches a state where, and it's hard to draw the two pictures, but basically your trampoline's gonna bend down and crazy Mike will be here. But we know that at this point where he finally reaches the bottom, well, eventually that velocity, it goes to zero, right? It kind of stops. And then as you're getting ready to go back up, you're going to start speeding up again. So you get to zero for just a tiny bit. This is going to be the velocity at bottom. And then as you go back up, if we started off down here, so we had zero, and now we're slowly going to kind of get pushed back up by the trampoline, right? And depending on how hard you hit that trampoline, it's hard to know how high up you'll go, but this is basically what's happening, right? So you got to ask the question, well, what is causing this change in velocity? And really, what we care about is really the moment when your body hits that trampoline. So when you hit that trampoline, let's so what we just did is we looked at the whole motion. but let's look at only moments in contact with trampoline. So at this point, we know when you hit that trampoline, you got a pretty high velocity, right? And then as you start bending the trampoline little by little, that velocity is going to decrease. You know, you keep slowing down even more and more as this thing stretches all the way. At some point, it's going to be velocity equals 0. And then we're going to start going back up again, right? And then finally, at the last point, we kind of bounce off of the trampoline back up, right? So you've got these decreasing velocity vectors. And the first hint for you guys there is, well, anytime you have decreasing velocity vectors, that means our acceleration is, you know, it's going upwards. It's against the motion. And this is being caused by the trampoline, right? So basically the trampoline is what's causing the pushing. When we get to the very bottom, well, that trampoline is still pushing on you, right? It's still pushing you upward. And we know that later times, it's going to keep pushing you up till you depart from the surface of the trampoline. So in this picture I just drawn, all of our acceleration vectors are pointing upward. And so for this one, the acceleration is upward. I know it can be a little bit maybe tricky to think about it, because when you're at the very bottom, like here, you're tempted to say, well, you know, everything's 0, it's not moving. But the reality is, if you look at the instant right before you got to the bottom, in one case you were pointing down in velocity, and a slight instant after you've reached the very bottom, now you're moving with an upward velocity. So that total change is a change in the upward direction. And remember, change in velocity is acceleration. So hopefully that kind of makes sense now. All right, so let's do a bunch of these quick checks. So here we have a cart slows down while moving away from the origin. What do the position and velocity graphs look like? So this is a little bit of review from last time, where they're asking us to look at the velocity graphs, the position and velocity graphs. So first of all, let's see what they're asking for. It just says the cart slows down while moving away from the origin. So that's a key thing to have to draw, right? So it says slows down and it's moving away. And we can see that it's moving away in the positive direction. So we start off with a big velocity. Because it's slowing down, it's going to be doing this. At the same time, position, this is X direction. We know our position's increasing, right? It's getting to larger points. So, but they are still positive. So let's see what you guys think here. Lots of D's. So first of all, let's look at the position. So in all cases, position has to be positive, right? We're just moving away from the X equals 0. So in that case, it's not going to be A, because that has negative values. Next thing is, we know that the velocity is decreasing, but it is positive, right? So velocity always positive, but it's decreasing. Which one is showing something like that? And so remember, velocity in this case is the green line. So for A, well, we already ruled out A. If you look at B, well, B starts off negative going towards 0, but we know it's always positive. So that means it can't be B. You look at C, also has negative values for velocity, so it's not C. You look at D, D kind of makes sense, right? You have, they're all positive velocities, they are decreasing, that's good. And we have because, and we have positive values for position. So in this case, the answer would be D. Okay. All right. Let's do another one. Hopefully we're getting better at this now. So here we have now the car is speeding up toward the origin. Once again, what do the position graphs look like? So in this case for 2020, now because we are moving towards the origin, all velocity are negative. It says it's speeding up, so V is becoming more negative. At the same time, because we're moving towards the origin, position X starts high and goes toward smaller value, towards 0. So if we look at these graphs, well, which one's going to do that? In this case, it turns out, as most of you have stated, the correct answer is C. And you could see for that one, you start off with a high position and it goes towards 0. And it has these velocities that are all negative and they're becoming even more negative, right? You can see as we depart and go towards negative V, those are just really highly negative magnitude velocities. Okay. All right. Let's do another one here. So this one's asking, so these are all very similar, but still related. In this case, now we're moving away from position and velocity, and now we're going to look at velocity and acceleration. So in this case, for quick check 221, it says the car speeds up while moving away from the origin. What do the velocity and acceleration graphs look like? So first of all, it's moving away from the origin in the positive direction. So we can say all velocity are positive. It's speeding up. So V is becoming more positive. So that's one bit of information. And because velocity is becoming more positive, that means the acceleration has to be in the direction that's also positive. So we're looking for a constant positive acceleration. And so in this case, a lot of you guys have said it's B, and sure enough, it's B. You can see here clearly, this is one that has all positive velocities that are increasing. There were 3 that did that, right? B, C, and D all did that. However, the question now is with acceleration, we want to make sure we have a positive constant acceleration. And so in that case, the other 2 didn't do that. We had this increasing acceleration, decreasing acceleration, but really we're interested in this one with a constant acceleration. In our class, we're not going to do many problems where you're looking at acceleration time graphs where acceleration is like has a slope to it. It's always going to be a constant, either positive or negative line for acceleration. So just FYI. All right, so here's another one. It says here, here's a motion diagram of a car speeding up on a straight road. What is the sign of the acceleration? So once again, you want to make sure you kind of look at all the reference points. So because we are dealing with a problem where, x equals 0 is on the left, positive x is to the right. So we're starting on the positive x-axis, and we're moving towards 0 with ever increasing velocity vectors. So all these velocities are negative, and because something has to help those velocities increase, well, the acceleration is what's helping those velocities get larger. And so you could see, because we have to point in the negative direction, then the acceleration along the x is negative. Okay. All right. So I know you're getting tired of these, but there's only, I don't think there's too many more. So here's another one. It says a cart slows down while moving away from the origin. What do the velocity and acceleration graphs look like? So once again, we're dealing with acceleration graphs, velocity and acceleration. So let's see, it says here, it slows down while moving away. And in the cartoon, we could see it's moving away from 0 and it's moving in the positive direction. So slowing down means we start off with a high velocity and these velocities getting smaller. So we can say all velocities are positive, and velocity is decreasing, right, in its magnitude. And so this will be what we use to help us figure it out. Essentially, because the acceleration, because the velocity is getting smaller, something's pushing against it, and that's going to be this acceleration that's going in the opposite direction. So we know we're going to have a negative value for the acceleration. So the next question is, well, which is the graph that does that? And a lot of you have chosen C, and you are correct. So you can see here, that's the only one that satisfies what I just wrote down. You want all positive velocities, and they have to be decreasing. So there's only B and C did that. But then the next part is to say, okay, well, which one has a negative acceleration? And that's where B gets ruled out, and then we pick C as the one that has that property, okay? All right, here's another one. So now we have a cart that speeds up while moving toward the origin, and how do the velocity and acceleration graphs look? So we're gonna do the same kind of exercise we've been doing all along. So we've got x equals 0. Well, because we're moving to the left, and it says that the cart speeds up. So we start off with a certain velocity, but now that it's speeding up, means these velocity vectors are getting bigger and bigger as you move towards 0. And so that means the acceleration has to be in that direction to help it grow in that direction. So we're going to get your accelerations are also negative. So we have to look at the problem that has all V negative and V speeding up. So V is increasing in magnitude. And this also means that you need to have acceleration is negative. So with those requirements, we find, so a lot of you guys have picked C. And C is the one that has that property, right? It has all negative velocities and they're increasing magnitude. So at later times, we are much more further away from V equals 0. So that's big magnitude. And that's the only one that has acceleration negative. So below the A equals 0 line, okay? All right, so now we're asked to think a little bit more about this relationship between acceleration and velocity. So they have given us the acceleration graph, and we want to know which is the corresponding velocity graph. So let's start that off. So we have acceleration, and initially, at the initial times, we're talking about a negative acceleration, and then suddenly we switch to a positive acceleration. So you want to remember that in this case, you remember that the slope of the velocity versus time graph is going to give you the acceleration. So when we try to figure out which is the correct velocity graph, well, we want to have a negative slope, and then we want to have a positive slope. So even before I put it on this graph, we know it's going to have to be a graph that looks negative slope, velocity, and then positive slope. We need to have a shape that looks like that in the velocity versus time graph. And so in this case, the only one that does that is the last one, which is E. And so you can quickly see that that is the only one that's correct. And so it's interesting because we could have put, so in terms of that graph in the slides, it kind of drew the shape kind of like that, which is fine. Um, indicating at time equals 0, we had a negative slope. But you could have also put it a little bit higher up. We could have said, well, maybe we were up at the top of this, we went down, and then we just changed our mind and went the other way. This would have been also an okay answer. The only thing that would distinguish, well, which one do you, I mean, like, you could ask, well, what if I had both of those graphs? Well, in that case, they would both be correct unless they gave you extra information. Like if they told you you started off in a positive velocity, then you know to shift everything up to the positive, okay? But in this case, they're basically saying we start off at velocity equals 0, and then we moved negative velocity, and then we switched and then started decreasing the magnitude with a positive acceleration. All right. So we've kind of gone through the whole process of, conceptually thinking about the relationship between velocity and acceleration. Some of the key concepts here with acceleration are that the slope of a velocity versus time graph gives acceleration. That's one of the key concepts. Now in this section 2.5, and so I'll introduce it, but we'll really discuss it a lot more in next time. We're looking at motion with constant acceleration. And so this, remember, this is acceleration is a vector. So some examples are things like rockets. Lately, there's been some news with the SpaceX rockets doing all sorts of cool things, and this gigantic thing that Elon Musk is testing out in Texas somewhere. And so this kind of science is alive and well. And so in this graph, they're showing you a plot of the velocity as a function of time. And so in this particular example, you can see how at a little bit around 0.5 seconds, we're moving at 10 meters per second. A little bit later, we go to between 15 and 20. And then after 2 seconds, we're all the way up to above or beyond 30 meters per second. And so the slope of this graph is going to tell us directly the acceleration. And so in their case, what they did here is they started the clock at 0.5 and they stopped the clock at 2 seconds. So in this case, start was t initial equal to 0.5. T final was 2 seconds. So the delta t in this case was 2 minus 0.5, giving you 1.5 seconds. Similarly, we have initial velocities and final velocities. So for that particular problem, it's kind of hard to read it, but it's at 0.5, maybe we were around 10-ish. And then the final was something like, I don't know, 30. I guess to make it equal, what they're saying is should be something like it's hard to kind of tell there, but either way, like when they did the delta V, they get a value of 27 meters per second. So that means this number here should have been something like 37 meters per second, which maybe it's not exactly right. But the point is to get the acceleration, remembering that it's delta V over delta T, you would take that change in these velocities, write it down up there, and then divide by the delta T, which is 1.5 second, and that would give you something like 18 meters per second squared, okay? That's just one example, but the whole point of this is we're gonna use this to develop our first equation of motion with constant acceleration. So let's just make another slide here. So we're gonna look at the equation of motion with constant acceleration. So I've already said acceleration is delta V over delta T. And even this, you can rewrite it so that it says delta V is equal to A times delta T. Well, if we remember that delta V is the final minus the initial, and stick it in there, well, we're going to have that final velocity minus initial velocity equals to A times delta T. So essentially, you can have an equation to solve for the final velocity after some time interval. And so in that case, what you would do is you just put the V initial to the other side. So I have V final is equal to the initial velocity plus A times the time interval delta T. And so this equation here, I'm going to call kinematic equation 1. So as we progress through the rest of this lecture, or through this next few slides today and in the next class, we're going to develop other kinematic equations. We're going to have a total of 3. And so I always tell students, if you were to identify some of the important equations for this class, these are some of the important ones. This first one I just wrote down, plus the other 2 we'll discuss. And so these are the ones that my physics teacher used to tell me, like, this is what you get a tattoo of, these are the ones that are not going to change for this course. Now, what's interesting is you can develop other equations using the properties we've already discussed. So we're going to use the fact that area of a velocity versus time graph gives displacement. So if this is the first time you hear this, I suggest that you go and look at the previous lectures, but this is important, and we've discussed this previously. So area of a velocity versus time graph is going to give us displacement. And so what we're going to look at more in depth next time is to see how does that actually work out. So if you have velocity, looks like this, and you've got some profile, it looks like that. Well, we already know slope is going to give us acceleration. But if you also remember, these velocity time graphs also tell us that the area under the curve gives us displacement. So we start off at some initial time, and we look at the motion up until some t final. The area that we have in here is going to give us the displacement delta x. And so what we're going to do in class next time is we're going to look at that more in detail to derive the next equations. But basically it means, because we want to find an area, well, we're going to have a little area of a rectangle down here, plus the area of this triangle up at the top. And we're going to find that the base is equal to delta t. The height of the rectangle will be some kind of initial velocity. The top of this triangle is going to be our final time. So this difference between initial velocity and final velocity, that's going to be our delta v. And looking at these equations that we just wrote, well, we also know that delta v is equal to A times delta t. So essentially it's going to be this area plus this area, that is going to give us delta x is equal to area of the first shape plus the area of the second shape. So, I mean, if you're interested in what I'm saying right now, go look at the rest of the slides, get familiar with it, but we'll talk about it with more detail next time, okay? So we'll carry on from here and we'll do some examples in class, more examples with more numbers that are more relevant to the homework that I've just assigned. Okay, guys? So that's all I've got for today. Is there anything pressing that you need to ask before we end class?
Professor, can you stand by a little bit after class for me, please?
Sure, I got a couple minutes.
It would only take 2 or 3.
Okay. Well, in that case, that's it, guys. So thank you very much. And we'll talk to you later. Well, you can ask your question now if you'd like, unless you want everybody to leave.
No, I don't care. I was just asking, I just accepted a new position. And I know before you mentioned that we don't have to attend this class and there's an alternate, I'm sorry, not attend the live session of the class, and there's an alternate means to it. I was wondering because right now I know I have to go back into work where with COVID, I don't currently have to go to work. So I was just seeing, I'm trying to see which classes I have to withdraw from to not run into collision and any issues.
Right. Well, I think for this class, there shouldn't be any, I mean, like I said, you have the option of just watching the videos later. If you have to leave early or if you can't join at all, that's fine. What you're doing right now is also okay. I would appreciate it if you could just send me an email just saying, hey, this is the situation. There are times where I might not be able to fully participate. Just put it in writing in an email so that I just have a copy of it because, you know,
Okay.
I don't want to forget at the end of the semester that you told me this.
Right. Yeah. No, that's perfect. I was checking because I remember beginning you mentioned that for those videos, if I watch later, how do I get the participation points?
So, so one of the things I mentioned in class before was in cases like yours where there's an issue, you know, whatever the circumstance, you're excused.
Okay.
You don't have to do anything extra. Just make sure you're keeping up with homeworks, and we'll discuss exams a little bit later, but I don't foresee there being a conflict, okay?
Perfect. Thank you very much.
Sure, you got it.
You guys have a good day.
You too, thank you. Is there another question from anybody? All right, well, if there's no questions, have a great day, guys. Bye-bye.